Imagine a tiny sphere, no bigger than a grain of sand, holding the potential to revolutionize energy production. This is the heart of inertial confinement fusion, ICF, a technology that LLNL has been refining for over half a century. The ICF target, a marvel of precision engineering, is meticulously placed inside a Hohlraum, a cylindrical container designed to focus laser energy. The target itself is suspended by a delicate membrane known as a tent, and is filled with fuel through a tube so fine it's 10 times thinner than a human hair. Even at these microscopic scales, every detail counts. Any minor imperfection can throw off the entire process, making the science behind ICF both fascinating and incredibly challenging. But here's where it gets controversial. The success of ICF experiments hinges on a sophisticated feedback loop between advanced simulations and real-world tests. This loop is powered by some of the world's most powerful supercomputers, which play a crucial role in predicting and optimizing experimental outcomes. From the early days of the Livermore ICF program, physicist John Knuckles recognized the importance of supercomputing in achieving ignition. His vision laid the groundwork for decades of innovation. From the single-beam Janus laser to the 192-beam National Ignition Facility, NIF, and from the CDC 7600 supercomputer to today's exascale behemoth, El Capitan. The laboratory's comprehensive suite of ICF modeling and simulation tools is a testament to this commitment. These tools encompass a wide range of physics, from laser-light interaction and electron transport to magnetohydrodynamics and fusion burn. By running millions of simulations and analyzing billions of data points, researchers can predict the outcomes of NIF experiments with remarkable accuracy. For example, ICF codes can simulate diagnostic measurements to validate experimental results, creating a continuous cycle of learning and improvement. As physicist Morty Rosen puts it, simulations are essential to ICF research. They allow us to design experiments with a level of detail that would be impossible without them. While NIF conducts hundreds of experiments each year, primarily for stockpile stewardship, only a small fraction are focused on achieving ignition. This scarcity underscores the value of simulations, which can significantly reduce the number of physical experiments needed. The higher the desired performance, the more critical it becomes to minimize any imperfections or asymmetries. To meet these demands, LLNL has developed a suite of proprietary ICF codes, including the long-standing Lasnex and the versatile HYDRA. Lasnex generation, Lasnex, created by physicist George Zimmermann, has been a cornerstone of ICF research since 1970. Initially derived from the one-dimensional Wazer code, Lasnex was the first two-dimensional code to simulate all aspects of ICF physics, including laser absorption, electron conduction, and fusion burn. Its early successes, such as simulating the first experimental proof of laser-induced thermonuclear burn, helped justify investments in laser technology. Over the years, Lasnex has evolved to include advanced models for X-ray transport and non-equilibrium atomic physics, making it indispensable for integrated Hohlraum capsule simulations. One of Lasnex's key strengths is its user-friendly interface, which leverages the basis scripting language. This allows researchers at LLNL, Los Alamos, and Sandia National Laboratories to customize their simulations, test sensitivities, and explore different physical processes. Lasnex runs efficiently on Livermore's capacity computing systems, making it accessible for a wide range of applications. HYDRA dynamics. In 1994, as NIF construction was about to begin, computational physicists Robert Tipton and Marty Marinak embarked on developing HYDRA, a new hydrodynamics code. Designed for massively parallel 2D and 3D simulations, HYDRA can model the entire implosion process, from capsule and Hohlraum physics to laser light and magnetic fields. Its flexibility comes from advanced meshing options and a Python-based programming interface, allowing users to integrate custom physics packages. HYDRA builds on the legacy of codes like Lasnex, continuing the tradition of ICF simulation leadership, says Marinak, now the project leader. Over the past 3 decades, HYDRA has achieved several groundbreaking 3D simulations, demonstrating significant advancements in both computational techniques and laser physics. These include simulations of Rayleigh-Taylor instability growth, high-resolution capsule dynamics, and detailed nuclear diagnostics in realistic geometries. The HYDRA team has adapted to the evolving landscape of supercomputing, ensuring the code remains portable across different architectures and memory spaces. During the petascale era, when Livermore's Sequoia supercomputer could perform 20 quadrillion floating-point operations per second, HYDRA delivered unprecedented 3D simulations of NIF capsules. More recently, the team successfully ran a test problem using 1/3 of El Capitan, confirming HYDRA's scalability to exascale systems. Predicting ignition. In the early days of ICF research, the tent inside the Hohlraum posed a significant challenge. As Rosen recalls, the tent was a major obstacle that compromised the original target design. In 2007, the codes lacked the resolution to address this issue. But by 2014, with the operational NIF and improved computational capabilities, HYDRA could accurately simulate the tent's impact. This led to a redesign that improved capsule performance, as confirmed by experimental data. Such advancements have been crucial in the journey toward ignition. Both Lasnex and HYDRA have been instrumental in predicting phenomena like Hohlraum reheating, a key indicator of ignition. This process, which occurs in nanoseconds, involves the lasers heating the Hohlraum, producing X-rays that compress the capsule's fuel and initiate fusion reactions. The resulting alpha particles deposit energy back into the plasma, leading to ignition. Lasnex and HYDRA predicted Hohlraum reheating accurately and in detail, confirms Rosen. Before the historic December 2022 shot, known as N22104, HYDRA simulations predicted a more than 2.5 times yield increase compared to the previous shot. The actual experimental yield fell within the predicted range, validating the models. Since then, LLNL scientists have achieved ignition multiple times, refining design variables to maximize yield. HYDRA has benefited from 30 years of experimental data, including the ignition shots, providing robust validation of its physics models, notes Marinak. Combined strengths. LLNL's computing power has grown exponentially since the development of these codes. The exascale El Capitan supercomputer, capable of processing more than 2 quintillion floating-point operations per second, is a game-changer for ICF research. We've come a long way, from rare 3D simulations to making them routine today, says computational physicist Luke Peterson. El Capitan allows us to achieve even higher fidelity simulations at larger scales. Cognitive simulation, CogSim, which uses AI to analyze simulation ensembles and experimental data, further enhances the ICF workflow. Trained on tens of thousands of HYDRA simulations, CogSim provides probabilities for experimental outcomes and helps optimize designs more efficiently. The IceCap project integrates simulations, supercomputing, and CogSim, expanding the ICF design space and predicting successful features from massive datasets. AI helps us answer questions we couldn't ask before, making ICF research more manageable, explains Peterson. Ignition and liftoff. With over 150 years of combined experience in ICF physics and computational modeling, experts like Marinak, Zimmerman, Rosen, and Peterson have witnessed the journey to ignition. However, ignition is just a milestone, not the end goal. Both Lasnex and HYDRA continue to evolve, adapting to NIF's mission and the laboratory's national security responsibilities. The HYDRA team is scaling up to leverage El Capitan's processing power and improving predictive capabilities, while the Lasnex team is developing new models for laser plasma interactions and non-local thermodynamic equilibrium. The multidisciplinary teams behind these codes understand the significance of their work. The physics is always intriguing, and there's always something new to discover in this field, affirms Marinac. It's gratifying to support researchers and contribute to the program's success. For more information, contact Marty Marinac at 925-423-8458 or at tipson.wyatt. Featured image. Run on Livermore's RZ Adams supercomputer. A HYDRA simulation shows density variations as the Hohlraum's interior is heated by laser energy. Credit: LLNL. This article was originally published by Lawrence Livermore National Laboratory, LLNL, and is reprinted with permission.